Every device connected to the internet requires an IP address. This numerical label serves a specific technical purpose, enabling decentralized routing across millions of independent, interconnected networks. The address executes two distinct functions simultaneously. It acts as an endpoint identity marker, confirming the exact device sending or receiving a payload, while providing the topological location coordinate required to forward data toward its destination. In the architecture of the Open Systems Interconnection model, combining identity and location into a single numerical label creates a design principle known as fate sharing. This diagram maps the OSI model, highlighting the network layer. Notice how the core internet routers operating here are entirely stateless. They evaluate the numerical labels on incoming packets, instantly forward them to the next hop, and immediately discard all memory of the transaction. Because the intermediate routers lack memory, the responsibility for maintaining the connection state is pushed entirely to the network edges. The endpoint devices themselves must verify that packets arrive sequentially and request retransmissions if data is lost. Decoupling endpoint identity from core state management prevents central routers from becoming overwhelmed by connection data. The internet scales efficiently because the core infrastructure remains stateless, though this architecture creates structural vulnerabilities when devices move and their topological coordinates change. The original routing architecture, Internet Protocol version 4, relies on a 32-bit format. This yields a hard mathematical limit of approximately 4 billion unique numerical addresses. To route traffic efficiently across a planet-sized infrastructure, the global address pool cannot be assigned randomly. Classless interdomain routing dictates that networks must be mathematically divided into smaller, contiguous blocks. This diagram visualizes how those blocks are defined. We see a standard 32-bit IPv4 address translated into binary, stacked over a subnet mask. The subnet mask determines the exact boundaries of the network block by designating which bits belong to the network and which belong to the individual host. Network hardware separates these values by executing a bitwise AND operation. The router mathematically compares the IP address against the subnet mask. Where both bits are a 1, the result is a 1. Where they differ, or are both 0, the result is 0. This calculation isolates the network prefix from the host identifier. Calculating the broadcast address for that specific subnet requires an inverse calculation. Hardware applies a bitwise NOT operation to the subnet mask, inverting the values, and adds the result to the network identifier. This rigid mathematical determinism allows physical routers to make instantaneous hardware-based forwarding decisions using basic logic gates, entirely bypassing the need to query external directories for routing instructions. The math functioned perfectly, but the capacity did not. The exponential proliferation of consumer broadband and mobile devices rapidly exhausted the original 4 billion 32-bit addresses. To prevent total gridlock, the Internet Engineering Task Force reserved specific blocks of non-routable private addresses, such as the 10. and 192.168 network ranges. These are strictly for internal local area networks and cannot cross the public internet. This diagram shows the required boundary between internal environments and the global network, Network Address Translation, or NAT. Multiple devices share private internal addresses. The NAT router acts as a border guard, translating internal identifiers and repackaging outbound data under a single public IP. Because dozens of internal devices might request data simultaneously, the router uses port address translation. It tracks internal requests by mapping them to unique transport layer port numbers on the external public interface, ensuring the returning data reaches the correct internal device. Not all translation models operate with the same logic. A full cone NAT allows any external server to send data inward once an initial mapping is created. Symmetric NAT applies a much stricter filtering model. Symmetric NAT creates a completely unique public mapping for every distinct destination a device attempts to reach. If an internal device tries to connect directly to another user on a separate network, the aggressive port randomization breaks direct peer-to-peer connectivity. This mathematical friction degrades latency-sensitive applications like online multiplayer gaming. When peer-to-peer connection fails, the translation gateway forces all data packets to relay through distant external servers, increasing ping times and destroying client synchronization. Network address translation successfully multiplexed a constrained resource and kept the internet functioning. However, By placing stateful translators between endpoints, it permanently altered the protocol's original end-to-end connectivity model. The structural solution to the heavily commoditized 32-bit market is Internet Protocol version 6. It utilizes a 128-bit architecture, providing an address pool large enough to eliminate the need for net entirely. Looking at this comparative breakdown, the newer protocol simplifies processing. The 40-byte IPv6 fixed header strips away optional fields and eliminates the hardware checksum, reducing the processing overhead required by intermediate routers. Optional routing instructions are now modularized through a specific next header field. The assignment methodology also evolves. Through stateless address auto-configuration, devices no longer rely on a central server to lease them an IP. They generate their own globally routable addresses by listening for network prefixes and combining them with locally generated identifiers. To prevent third parties from using these static identifiers for surveillance, IPv6 utilizes privacy extensions. Operating systems constantly generate rotating, pseudo-random addresses that frequently expire. This mathematical obfuscation prevents external entities from tracking user movement across different access points. The expanded address space also scales complex routing topologies. Under anycast routing, the exact same numerical IP address is legally assigned to multiple geographically dispersed servers across the globe. When two users ping that identical address simultaneously, the Border Gateway Protocol calculates the topological distance. The underlying algorithms automatically route the request to the physical server instance nearest to the user's location. By ensuring data travels the shortest physical distance, Anycast drastically cuts latency for content delivery networks. It also provides inherent structural defense. In a distributed denial-of-service attack, malicious traffic is absorbed by localized edge nodes, preventing a botnet from overwhelming a single centralized server. The original Internet architecture prioritized connectivity over verification, built on implicit trust. Because standard packets lack cryptographic authentication, malicious actors can easily forge the source address in a packet header, a vulnerability known as IP spoofing. This implicit trust extends to the global routing infrastructure through Border Gateway Protocol hijacking. The Internet relies on decentralized autonomous systems announcing which blocks of IP addresses they control. This diagram demonstrates the attack vector. Routing algorithms inherently prioritize highly specific prefix lengths. If a rogue autonomous system broadcasts a forged claim, providing a faster, specific route to a target IP block, the surrounding global routing table updates to prioritize the attacker's path. By exploiting the mathematical priorities of the routing algorithm, the attacker successfully hijacks the traffic, funneling massive streams of legitimate data into unauthorized destinations for interception or disruption. Solving these vulnerabilities requires two distinct cryptographic frameworks. For the data payload, IPsec utilizes authentication headers and encapsulating security payloads to provide origin verification and end-to-end encryption. For the topological routes, network operators deploy the resource public key infrastructure. This system enforces route origin validation, requiring an autonomous system to provide a digitally signed validation, proving it mathematically owns the addresses it claims to route. Securing global digital infrastructure requires stripping away the assumption of trust. Modern architecture demands strict cryptographic signatures for both the endpoint payload and the topological route. The IP address remains the foundational element of global telecommunications. It operates simultaneously as an endpoint identifier and a topological compass, providing the necessary link between hardware and geography. The shift from the 32-bit architecture to the infinite scale of 128-bit routing replaces the friction of network address translation with automated, privacy-focused configuration. Simultaneously, the global routing table is shifting from a system of trust-based broadcasting to a framework of cryptographic validation. These architectural realities dictate the user experience. The utilization of Anycast topologies determines how fast a web page loads by calculating the geographical distance of a data request. The strictness of a local NAT gateway determines peer-to-peer traversal, making the difference between seamless synchronization in competitive gaming and severe packet desynchronization. This architecture is now a commoditized, cryptographically secured asset. Its ongoing development ensures the performance of the digital infrastructure we rely on every day.
Thank you so much for watching. If you enjoyed this, please subscribe, like, and share. And don't forget to hit the bell for more from Tech AI and beyond.